Next, we will start our study of the implicit function theorem. Firstly, we consider most simple case, that is the Dini theorem. The Dini theorem, the more general implicit function theorem, concerns this question. Given an equation f(x,y) is 0, we want to solve y using x. Can we solve f(x,y) equal to 0 to obtain y? Of course, the y must depend on x. Okay, this is the question we want to study. Now we consider a simple example. f(x,y) is x squared plus y squared minus 1. Then suppose fab is 0, and we consider the case b is not 0. So geometrically, this is the coordinate axis, x and y, and fxy equal to 0. Fxy equal to 0 is the graph. Geometrically, it represents a unit circle, right? And fab is 0 means that the point AB is a point on this circle. So AB is here. Now we consider the case B is not 0. Now geometrically we see that we can find a small epsilon. We can find a very small epsilon, so that there exists an epsilon positive small, so that for any x in a minus epsilon, a plus epsilon, for every x near the point A, we have a unique y, so that xy is on the circle. Okay. Or in other words, we have a unique continuous function y from a minus epsilon, a plus epsilon, real valued, such that ya is b. The value of the function at the point A is ejected over B, and capital F x y x is 0. Okay, this means the graph of this y lies on the curve fxy is 0. The graph of this function is here. The blue part of the circle is the graph of this function, and such a continuous function is unique. Okay, actually this y, we can write the expression for this y. Y is minus 1 minus x squared. Okay. Of course, we have another continuous function such that f(x, y tilde) x is 0. The y tilde is minus 1 minus x squared. But that function, the graph is here. That function does not pass the point AB. Actually, it passes the point A minus B. Okay, so only one continuous function passing the given point AB, and satisfies the original equation, capital F(x, y) x is 0. satisfies this. Okay, so such a function is called implicit function. Many functions could not be defined explicitly, but they can be defined implicitly. For example, using an equation capital Fxy equals 0. Okay, so this is the case for b is not 0. For b equal to 0, say for this point, minus a 0. For this point, no matter how small the neighborhood you take, no matter how small epsilon you take, you could not define a function in the if b is 0. So if b is 0, then a is positive or negative minus 1. Okay, so this is minus 1. And in this case, no matter how small the epsilon you take, you could not define a function. There is not a function y from a is minus 1 or positive 1. So minus 1 minus epsilon and minus 1 plus epsilon, such that capital F x yx is 0. You could not have such a function because all the points allowed in the graph of the capital F in the circle, in the unit circle, the unit circle does not contain the point which x coordinate less than minus 1. All x must be greater than equal to minus 1 or 1. All x must contained in this interval, minus 1 and 1. So you could not have y defined in any neighborhood, small neighborhood, no matter how small the neighborhood is, the y could not be defined. Because every such neighborhood contains points whose x coordinate is less than minus 1. Therefore, such point could not satisfy this. So this means when b is 0, then the previous conclusion, the previous existence of such a function small y is not true. So what's the difference for b equals to 0 or b is not 0? Now consider this equation. Now this function capital F. We see that the partial derivative of capital F at the point AB is precisely 2b. So whether b is 0 or not, simply equivalent to the derivative, whether the derivative with respect to y is 0. So it turns out that this is actually the crucial condition to determine whether we can define a function implicitly from the given equation. Okay, so this is the Dini theorem we will discuss below. Theorem. Dini is an Italian mathematician. Was an Italian mathematician. Suppose F defined on this rectangle is say 1, and we have a point AB contained in this rectangle. So that FAB is 0. Okay. Now our purpose is to solve from fxy equal to 0. From this equation, we want to solve y as a function of x. This is our purpose. This is our purpose. When can this be possible? So the condition is that if the partial derivative with respect to y at the point AB is not 0, then there exists some r positive and a function phi defined in an R neighborhood of A, alpha A. Such that the following property are satisfied. So the first one is that phi A is B. Phi A is B is crucial. Otherwise, such a function phi cannot be unique. We want a unique solution. Therefore, we need some condition to determine which solution you take. Okay. The second is that capital F x phi x is 0 for any x in the neighborhood A minus R, A plus R. Okay. These two conditions are natural because our purpose is to solve fxy equal to 0 for y, express y by x. Now y is a function of x, we denote it by phi x. Okay. The third conclusion is that if x is close to A and y is also close to B, and xy satisfies the equation capital F is 0, then y is phi x. This means given x near B, near the value or near the point B, there is only one y satisfying the equation. This is a uniqueness conclusion. Okay. If you do not want the uniqueness without this property, without requiring the function phi satisfying the third property, we have more than one. We could have more than one. For example, in our unique circle example here, for the A here, we have this pair of function y and y tilde. Both y and y tilde satisfies the equation, satisfies the capital fxy equal to 0. Of course, y tilde does not satisfy fxy. Y tilde does not satisfy y tilde A is minus B. Is B. This is y tilde A is minus B, so it could not satisfy the y tilde A equal B. But it satisfies the capital fxy equals 0. Okay. And this function is C1. I forgot to mention that the function phi we declare its existence is C1. I forgot to mention this. Okay. So this is the Dini theorem. So our purpose is to prove this theorem for today's